So we saw Fourier series properties, what happens to the Fourier series coefficients when the time domain signal has certain kind of symmetry, right? Now, what if you modify the time domain signals? What are the standard modifications that we know? We know time shift, time scale, time reversal, conjugation and all those things, right? So what if we do these operations in the time domain? Then is there a corresponding simpler operation on the Fourier series coefficients? It so turns out yes, and we'll see what they are. So what if you take the conjugate of the time domain signal? So for all these analysis, we of course need the decomposition. What is the Fourier series decomposition? It is just simply representing everything in terms of the phasors. We represent that. So you take the conjugate one side, which is taking conjugates on the other side, which just tells you that this is a star e power minus j k omega t. Okay. Now just replace this, let's say in this summation k runs from minus infinity to infinity. Now let's say I am just going to change this index variable. I'll call another variable m, which is equal to minus k, which means now z star of t is summation m, which is equal to minus infinity to infinity a minus m, just replace k with minus m, okay, star e power, this minus k here now could be just replaced with j omega mt. Now compare this and this, okay. The phasors are now exactly the same, e power j k omega t and e power j m omega t are the same, because m runs from minus infinity to plus infinity, k also runs from minus infinity to plus infinity. So comparing this equation and this equations, we can equate their coefficients, and the coefficients simply now become that a minus m star is equal to ak, or in other words am is, so now we get the Fourier series coefficient of z star of t in terms of the Fourier series coefficient of z of t. So this is the Fourier series coefficient of z star of t, and this is the Fourier series coefficient of z of t. So if z of t has Fourier series coefficients given by ak, then the Fourier series coefficient of z star of t is simply nothing but a minus k star. So when you take the conjugate, what happens to the Fourier series coefficients? The Fourier series coefficients not only get conjugated, but they get reversed in terms of frequency. That is, if let's say 10 radians per second had a coefficient of ak, when you take the conjugate, minus 10 radians per second will have that coefficient conjugated. Okay. So there is a flip, like similar to time reversal, there is a spectral reversal here. Okay. Whatever was the spectrum on the right hand side moves to the spectrum on the left hand side, and the other way around if you simply take conjugation. Okay. Now what happens if you actually do time reversal? So if you do time reversal, then it is very simple to analyze what's going on. So what we do is just simply replace t with minus t. So if you simply replace t with minus t, z of minus t is equal to ak e power minus j omega kt. So we'll do the same thing like before. We'll simply now replace this index with m. So replace this index with m, that is, say that m is equal to minus k, then we have a minus m e power j omega mt. Now compare the coefficients here, and when you compare the coefficients here, you can say a minus m is equal to ak, and you can say that am is equal to a minus k. So whenever there is time reversal, the Fourier series coefficients also have a spectral reversal. So this is what we refer to as spectral reversal. Whatever is on the left hand side of the spectrum goes to the right hand side and the other way around. What happens to the bandwidth in these two cases? whatever was the maximum frequency still remains the maximum frequency. Whatever was the minimum frequency still remains the minimum frequency. So the gap between the maximum and minimum frequency does not change. So in both these cases, when you take the conjugate or when you reverse the signal in time, the spectrum does not change its bandwidth. The bandwidth remains the same. So what happens when there is a time shift? So intuitively thinking, the time shift does not change the period of the signal. Because the period of the signal is not changing, the frequency of the signal should also not change. Then the frequency components in the signal should also exist, right? All they have to do is they probably are now starting at a different point. So if a particular signal was starting at 0 because of time shift, it might be starting at now 1.2 seconds, or it might be starting at -3 seconds, and so on. So the phase in which the periodic signal starts has changed, but the frequency itself has not changed, the period itself has not changed. So intuitively we would expect only a phase change, and that is what we will see in our analysis also. Same thing goes for time reversal. So when you time reverse a signal, you would not expect the signal's period to change, you would not expect the signal's frequency to change. So the frequency component should remain exactly the same. But when it has earlier started from left to right, now we have flipped from right to left. So which means something which was going in clockwise because of time reversal is now going in anti-clockwise. You reversed time, right? So which means positive frequencies become negative, negative frequencies become positive. That's exactly what we saw. So the intuition completely follows the analysis. Z of t is equal to the real part of Z of t plus j, imaginary part of the Z of t. Okay. So when you take the Fourier series is now just decomposition of Z of t, which could be now considered as decomposition of Z r of t separately and decomposition of j z I of t separately. So the decomposition of Z r of t will give you a conjugate symmetric part because the real signal. This is purely imaginary, which will give a conjugate asymmetric part. So this decomposition will not change when you take the conjugation, whereas the sign of this decomposition changes. Okay, and that is what you see here. Alright, so let's see analytically what happens when there is a time shift. So when there is a time shift, let's say we are shifting by some minus s. Let's look at this equation. What happens in this Fourier series computation? So Z of t minus s is a k j omega t minus s. In other words, what happens here? So this is the phasor of frequency k omega. All we are doing here is we are adding a phase shift to this phasor. So you can say that this is e power j omega ks. So this is not a function of time. So e power j omega ks is a complex number. So given omega, given k and given s, this is a fixed function, or this is a fixed number. It does not change with time. So you can just club that with a k, okay, and you can say now this is the phasor. So all you are doing is you are starting the phasor with a phase shift, with an offset, and that offset is given by this s. That's all. So the frequency component itself is not changing, meaning the frequency of the existing components remain as such, but the amplitude of the frequency component changes. The magnitude does not change, the phase change. Because the phase changes, the amplitude can change. Keep this in mind. The magnitude remains still the same. So the magnitude of AK is still the same, but the phase has changed, because of which the real and the imaginary components change. So the amplitudes of real and imaginary components will change. So only the phase changes. Bandwidth does not change because the frequency components are not affected. Only the place where they start changes. Okay. Now what about time scaling? So we already saw what happens when there is time shifting. What happens when there is time scaling? So we know that when we time scale a signal, it either compresses or expands. So when does it expand? If there is an expansion in the time domain, so it means that c is less than 1, there is expansion. and C is greater than 1 implies there is compression in the time domain. So, if I have a signal which is, let us say, looking like this, -1 to +1, if I stretch it, then this is what I get. So, of course, we are talking about periodic signals. So, let us say we have -2 to +2 and so on. Whereas, if I shrink it or compress it, then maybe this is what I will get. So, when the C is less than 1, we end up getting an expansion like this here. When C is greater than 1, we shrink it. As you can see here, the period expands when there is an expansion. Because the period expands, what happens to the frequency? Frequency reduces. How often the signal repeats itself has reduced now, which means the amount of frequency which was higher earlier now becomes smaller. So, if it was of 1 radian per second here, now it becomes half a radian per second. Whereas, in the case of shrinking, the period has reduced, which means it occurs more frequently, which means the frequency has increased. So, whenever there is an expansion in time, we expect the frequency to reduce, and whenever there is a shrinking or compression in time, we expect the frequency to increase. This is our intuition, and in fact, this is what will happen also. Let us see what happens when we have time scaling. So, we have a k e power j omega k c t. So, as you can see here, we have scaled in time. This coefficient does not seem to be changing, but the frequency of the phasor has changed. So, if ak corresponds to the coefficient of the phasor with k omega t here, then what is the corresponding coefficient for e power j k omega t when the signal is compressed? Let us call this signal as some v of t. Okay. If v of t is equal to some bk e power j k omega t, then what is the relationship between ak and bk? How are they related? So, once again, what you can do is you can compare the coefficients here, right. So, the coefficients of e power j omega t should be the same. So, if I fix, maybe we can reduce confusion, we can say, now we can compare the coefficients. So, e power j omega t should have the same coefficient right, which means that m is equal to, or in other words, Bm is equal to A m by c. Okay. So, if this is true, okay, then for what value of k this is true? The value of k for which this is true such that m is equal to k by c. Okay. So, k is equal to m by c. So, then we get this relationship. That is, now the Fourier series coefficients of z c of t, that is the time scaled version, depends on the Fourier series coefficient of z of t in this manner, where the Fourier series coefficients get advanced or postponed. Or in other words, the way to see this is that the fundamental frequency itself has changed. So, remember we said the omega that we take here is the smallest frequency component that is present. That is, it corresponds to the largest period that is present. So, when you expand or when you shrink the signal, the fundamental frequency itself changes, the fundamental period itself changes. So, earlier whatever was omega now gets scaled with c omega. So, you can either see this as where the coefficients change or where the fundamental frequency changes. So, whatever is omega here, you can now redo this analysis with saying that now I am going to decompose the signal with a different fundamental frequency. So earlier I decomposed the signal with fundamental frequency omega. Now I am going to call some other omega naught as some c times omega. Now given that our new fundamental frequency is now omega naught, let us say that we are going to decompose this signal in terms of the new fundamental frequency. Let us say bk e power j omega naught kt. Then if you compare these two coefficients here, then you can directly say that ak is equal to bk, right? The Fourier series coefficients are now exactly the same for these phasors, because these two phasors for k is equal to 1 are exactly the same. So the Fourier series coefficients do not change, but the fundamental frequency changes. So if you fix the fundamental frequency in both these decompositions, then the Fourier series coefficients would change. They'll either move apart or they'll come closer together. If they are coming closer together, it means that the frequency components are becoming smaller and smaller, which means the signal has been actually expanded, and the other way around. Okay, so you can see this as two different things where you have changed the phasors itself. So basically what is this? This is a decomposition of a signal in terms of phasors with certain frequencies. Now what if we change these frequencies? Earlier, let us say if my frequency of the phasors were plus or minus 1, plus or minus 2, plus or minus 3, now I can change them to plus or minus 0.5, plus or minus 1, plus or minus 1.5, and plus or minus 2, and so on. So this is one set of phasors. So the moment I've changed this, what I'm saying is this time scaling would give me the same coefficients for this expanded set. Or I can now say that my original set of fundamental frequency has not changed, but I have moved the coefficients alone. So there are two ways of seeing this. With a very simple example, now let us say that z of t is a complex signal. So what if we just want to consider z of t as a phasor itself? So what if z of t is just a phasor, e power j t? Okay. Now if I am going to expand this in terms of my Fourier series coefficients, what is my Fourier series coefficients? ak e power j k omega t. Now let us say my omega is 1. Okay. So my omega is 1, which means I substitute that here, I just get kt. Now what are the values of k here? K is running from minus infinity to plus infinity, but ak is equal to 1 for k is equal to 1, 0 else. That you can directly observe, right? Because you just compare the coefficients and you can say that when ak is equal to 1, you get the signal that we have. For all other phases, those components do not exist. So there is a very simple example where we have time domain signal and we have the corresponding Fourier series coefficients. Now what if we expand this? Let us say I expand this to 2t, or in this case I have compressed it because this is the scaling factor is greater than 1. So I have compressed it in time. So this becomes j2t. Okay. Now what is the corresponding Fourier series representation under the old fundamental frequency? Under the old fundamental frequency, now I will say that ak is 1 for k is equal to 2, right? In all other places it is 0. So what happens when we change the fundamental frequency? So let us say we change the fundamental frequency, omega is equal to 2, then the representation is sigma ak e power j 2 kt, right? Now what is the Fourier series coefficient for this? The Fourier series coefficient of z of 2t. The Fourier series coefficient of z of 2t is ak is equal to 1 for k is equal to 1, 0 else. So as you can see here, these two are exactly equal. Fourier series coefficients are exactly the same, but the fundamental frequency has changed. Okay. So this is one way of denoting this representation. Or the other way, maybe here let me change this coefficient so that it's easier to understand. Okay, now the other way here is where you have a different coefficient but the same fundamental frequency. Now the coefficients are different, and remember what was the relationship we had? Bm was equal to A m by C. So for m is equal to 1, we have a 1 by 2 which does not exist. So when m is equal to 2, we have a 2 by 2 which is equal to a 1 for m2. That is exactly what we got here. So when there is time scaling, you can have two different notions of Fourier series representation, where in one notion you can change the fundamental frequency and say that my Fourier series is exactly the same, or you can retain the fundamental frequency and then change the coefficients. Okay, and both are equivalent. All we have to finally say is that what are the phasors that are present, that is, what are the frequencies of the phasors that are present, and what are the corresponding magnitudes. That's all we need. Basically, you are decomposing everything in terms of phasors, and to describe a phasor, we need its magnitude and its frequency. That's all. And how we represent that, it's up to us. So we can have multiple representation. In this case, we saw two different Fourier series representation for the same signal by having different fundamental frequencies. So I can change the fundamental frequency and then keep getting different representations. But note that we cannot arbitrarily change the fundamental frequency. So if I have, if the smallest fundamental frequency that is present in the signal itself is, let's say, 2 radians per second, then I cannot reduce any more, meaning I cannot represent the signal with fundamental frequency of 3 radians per second, because the fundamental frequency of 3 radians per second and its harmonics are plus or minus 3, plus or minus 6, plus or minus 9, and so on. But if my periodic signal has a fundamental frequency or has a frequency component which is equal to, let's say, 4 radians per second or 2 radians per second, I cannot represent that with this set of phasors. So if I have 4 radians per second, then I can probably represent that with a fundamental frequency of 1 or 2 or 4. So if I have fundamental frequency of 1, then its harmonics would be plus or minus 1, plus or minus 2, plus or minus 3, and so on. So I can represent 4 radians per second with that. Now if I have fundamental frequency of 2, then its harmonics would be plus or minus 2, plus or minus 4, and so on. Once again, I can represent 4 radians per second with that. If I have a fundamental frequency of 4, then I'll have harmonics of plus or minus 4, plus or minus 8, and so on. Again, I can represent 4 radians per second. But if I have fundamental frequency of 3, then my harmonics would be plus or minus 3, plus or minus 6, and so on. I cannot represent 4 radians per second with that. So if you want to represent a particular frequency component, keep in mind, then we need some harmonics of that to be present in our choice of phasors.